Hello, so in this video we are continuing our work with our SUVAT. So when we're in situations where we want to find the displacement, the velocity, the acceleration, the time, stuff like that, right? So we're gonna look at some more equations today in this video. So I'm just gonna introduce it by looking at this example here. Okay, so we're given a velocity time graph of something, right? We're given quite a generic velocity graph, right? We have the initial velocity u, the final velocity v. So again, it starts here at u and then it ends here at v. The change in velocity is going to be v minus u, and it's over time. So this is my change in time, right? And so what I want to first show using my graph are these two formulas here, which I've done last time. We've seen these formulas last time. You should be fairly familiar with them. And so very quickly, because I did go over it last time, v equals u plus at. Well, actually, to show that formula, again, we know that the gradient represents acceleration, right? And the gradient is going to be the change in velocity over change in time, right? That's when we looked at velocity graphs. And so actually, if I call the acceleration just a is going to be change in velocity, but the change in velocity is just v minus u, right? And then the change in time, well, it just goes up to t. It's t take away 0, which is just t, right? So t take away 0 is just t. And then if I multiply, I get at is v minus u, and then if I add u to both sides, I get v is u plus at, and there's my formula there. Okay, now I'm going to prove this formula here. So we want to say that s is u plus v over 2 lots of t, okay? Or we could say a half lots of u plus v lots of t, okay? So, okay, how are we going to sort of get this formula? Well, it's the s is the displacement, right? Which means it's the area under the graph, okay? Now, we have a trapezium here. So again, if I get rid of these, so my trapezium, my parallel sides, here and here, well, this length is just u. This length is going to be u plus v, right? No, sorry, v, just v, right? Goes up to v. And then here is t, okay? And so very simply then, my trapezium, the area of this trapezium, the area under the graph, is going to be a half of the parallel sides, so u and v, times by t, and that's literally the formula. So the area represents displacement. So s for the displacement for the area is then if I bring the half in the bracket, I get u plus v all over 2 times by t, which is the formula they wanted there. Okay, and so if I summarise, I got v is u plus at, and also s is a half of u plus v lots of t, okay? Okay, now what we're going to look at are proving other formulas we can use, okay? So we need to show these 3 formulas here, okay? So we don't need the graph for this anymore, because what we can do is we can, using these 2 sort of original equations, I can derive more. So I first want to show that v squared is u squared at 2as. So my aim is to show that v squared equals u squared plus 2as. Okay, so where we're going to start, okay? So again, these are sort of simultaneous equations in a way. But okay, so how I'm going to use these 2 equations to get this equation here? Let's think about it. This equation doesn't have a t in it. It doesn't have a t. What I can do here is I can rearrange one equation to substitute t in. Oh, let's pick this one. This one's the simpler one. So if I take v is u plus at, Therefore, if I rearrange for just t, which I'm going to substitute to eliminate it, then v minus u divided by a is going to be t. So therefore, if I substitute t into here, I'm going to get s as a half of u plus v times by t, which is v minus u over a. Okay, so then at that point, if I multiply it, I get s is a half of u plus v, then v minus u over a. Okay, if I multiply these two sort of fractions, these two brackets here, what hopefully you notice we have up here then is a difference of two squares. If I rearrange this ever so slightly, v plus u, v minus u, hopefully it's very clear now. This is a difference of two squares, so I can expand it, right? I can expand it. So I get half of the top bit, which if I expand is going to be v squared minus v squared minus u squared over a. Okay, and so if I look at this equation again now, I want to get v squared. I want to get v on its own. So here I got s in terms of v, u and a, but I want to get v on its own. So let's rearrange. So firstly, I'm going to need to divide by half. Okay, so that would be if I divide by half, that'd be essentially times in by 2 to get 2 lots of s. That's going to be v squared minus u squared over a. Then if I times by a, I get 2af. It's going to be v squared minus u squared. And therefore, v squared, if I add u squared, I get u squared plus 2as. And that is what I wanted to show. Okay. Okay, let's have a look at the next equation. So what do we need to prove now? We want to show that s is ut plus half at squared. Okay, so what do I notice here? There's no v involved. Okay, so again, if I look at these two equations here, in fact I'll circle them. So I don't want any v's, right? V is not in this equation here that I want to show. So I'm going to need to not rearrange for t, but rearrange for v. And actually that's quite easy because this is already in terms of v, right? V is u plus at, but v is already the subject, right? So if I substitute v into here, so that means s is going to be a half of u plus v times t. Well, that means if v is u plus at, then that means s is a half of u plus at times t. Okay, and then if I just clean up inside the bracket, I get s as a half of 2u plus at times t, and then if I expand the brackets, so this is going to be s is a half times 2u. A half times 2 is 1, so it's just u plus a half at, okay, times by t outside. Then if I just times by t at the end here, s is going to be that's a plus, so it's going to be ut and a half at squared if I just multiply everything in the bracket by t. And that is what I wanted to get. That's my other formula. Okay, last formula I can show. I want to end up with s is vt take away half at squared. Okay, so what do you so what am I missing here? I'm missing the u. I don't want a u in this equation. So if I again stare at these two equations that started with, I don't want a u in. I'm going to need to substitute u in. So I'm going to rearrange this equation, v u plus at. I'm going to rearrange to get u the subject. Okay, so if we start with v is u plus at, therefore u is going to be v take away at. And so therefore, if s is again a half of u plus v times t, then that means s is going to be half of u, which is going to be v take away at, add v, times by t. And then if I just clean up inside the bracket, that's going to be half of 2v take away at times t. Then if I times by half first, a half inside the bracket, so 2v times a half is just v. And then take away a half, lots of at, times by t. Then lastly, if I times it out by t, I'll get vt take away a half at squared. And I reckon that's the equation I needed to end up in. And so there we are. Okay. And so actually what we found now are 3 more formulas I can use to work with these sort of problems with acceleration, displacement, stuff like that, where we can find a missing time, missing displacement, missing acceleration, missing velocity, right? So I've got more equations to help me. And so what's the purpose of this? Well, if we looked at these 2 equations last time, so this equation here, VU plus AT doesn't have S in. This equation doesn't have A in. But what about if we don't care about U, T, or V? Well, actually, then this equation doesn't have a T in. So this equation doesn't have a V in. This equation doesn't have a U in. So now we've found 5 different equations, which means we don't need to care about one particular thing. Okay, we only need. So obviously we got SUVAT, right? S is displacement. U is initial velocity. V is final velocity. A is acceleration. And T is time. So what we've effectively ended up in now, because of these 5 equations, I don't need all 5 things. Okay, there's always an equation I can use where I can dismiss one of these. Okay, so I only need 4 of these at one time. Okay, and so why am I bothering with this? This sort of like derivation. You need to know how to derive these equations. Okay, it's in the specification. You need to understand, use, and derive these formulas here. Okay, now they're not going to be mean or just completely say from scratch, prove this. Okay, they're not going to say just with nothing, prove it. They're going to set it up like with this question. They're going to aid you. They're going to set up the problem, right? They're going to give you a graph, or they're going to give you some equations to work with, but you need to be able to derive them, kind of like what I've done here. Okay, so you do need to pay attention to what I've done here, but hopefully that made some sense. So yes, you can use a velocity time graph if you consider the acceleration and the area underneath, and also you can just substitute equations together in this way. Okay, but you do need to be able to derive them. Okay, work out and get these equations. Okay, and you'd also be glad to know that whilst yes you do need to be able to work out these equations if asked, you are given the formulas. However, okay, so you don't need to memorize the formulas. You need to be able to work them out. In the rare case they might ask you to, but you don't need to memorize the formulas. You are given all 5 of these. Okay, all 5 of them, and it's quite interesting. This is the only formulas you're given in all of mechanics in year 1 and year 2. So I don't know, you can be grateful for that, I guess. But these are all the formulas here, so you don't need to learn them. Okay. So that's some good news. Okay, so with that in mind, let's have a look at some questions. So here we are told a particle is moving in a straight line from A to B. So again, I'm just going to draw my sort of line, right? And let's say A is here and B is here. Right, and it says constant acceleration 5. Okay, so my acceleration, a double arrow, that's how I represent it, with 5 meters per second per second. The velocity at A, the velocity is 3 meters per second. I'll write it down there. in the direction A to B. So that's all that's saying is it's going from A to B that way. Okay. The velocity at B is 18 meters per second. Okay. It says find the distance A to B. So what is this distance here? Okay, so we've got a bit of information here. So again, the strategy is I'm going to list my SUVAT. So what do I need or what do I want? What do I have? Well, S is my displacement or my distance. So, okay, well, that's what I want to work out, right? I want to work out the distance. Okay, question mark. U, the initial velocity is 3. The final velocity at B is 18. A, my acceleration is 5. And my time, I don't care about, okay? And I'm not giving it either, okay? So, again, I only need 4 of these 5 things. So, I'm dealing with 4 of these quantities. Okay, so let's have a look at which formula I can use. So, because I don't care about T, T's crossed off, right? I want the formula that does not involve T. Which one of these does not include T? This one here, V squared is U squared plus 2AS. And now you'll see why it's useful to work out the other formulas, because if we only use the 2 formulas we worked with last time, we'd have to do extra work, because then we'd have to find T and then find S. But now we've worked out more formulas, we can just jump right to this, okay? So, okay, we want to find S, so let's just substitute these values into this formula. So V is 18. 18 squared is U squared, which is 3 squared. Take plus 2 lots of A, which is 5. Lots of S, which is I'm going to call X. Okay. Okay. There we are. So at that point, it's just solving an equation. Well, 18 squared, firstly, is 324. That's going to equal 9. Add 10x. So if I solve for x, so 10x is going to be 324, take away 9. That's 315. So therefore x is 315 over 10, which is 31.5 meters. So that is my distance from A to B. Okay, 31.5 meters. And that's it. Okay, that's it. Okay. Okay, so we've got this question here. So here I'm told a particle is moving in a straight horizontal line. So again, just some line, right? With constant deceleration 4 meters. Okay. So that means the acceleration, well, it's not going to be 4 meters. It's going to be negative 4 meters. Okay, meters per second. Deceleration, again, remember, means negative acceleration. And so what that means is it's slowing down. Okay, the speed will be going down. Okay. Anyway, so at time t is 0, the particle passes through a point O. So let's say O is here. With speed 13. So initially it moves at 13 meters per second. And it travels towards a point A. Let's say A is here. Okay. And I'm told the distance O to A, the distance is 20. Okay. There we are. 20 meters. Right. Then it says find the times when the particle passes through A. Interesting. Plural. Which suggests that it'd be passing through A 2 times. Okay. Now, okay, so again, we want the time it goes from O to A. So time, I don't know. But what I do know is the distance. I know the initial velocity and the acceleration. Okay, so let's work with those. So if I list by SUVAT, S is going to be 20. U, the initial velocity is 13. V, well, the velocity at A, I don't know anything about. I don't care about it, really. A, the acceleration is -4, because it's deceleration. And T is what I want to work out, okay? So, which formula, because I don't care about V here, which formula, if we look at here, these 5 formulas, which one does not include V? It's going to be this one here, right? S is ut plus a half at squared. And so that's the idea with selecting a formula. Which formula does not include the variable you don't care about, okay? So this one does not have V in, so if I sub my values in, 20 for S is going to be, and U is 13, so 13 lots of T, add a half lots of A, which is minus 4 times T squared, okay? So if I simplify this, I get 20 is 13T, and then a half times minus 4 is minus 2 T squared. Interesting, we get a quadratic, right? So if I add T squared, 2T squared, I get 2T squared, take away 13T, add 20 equals 0. If I just move one each side to the other. And so I need to solve, okay? So T is going to be, then if we use the formula, 13 plus or minus the root of minus 13 all squared. Take away 4 lots of 2 lots of 20 over 2 lots of 2, and so that's going to get me, I'll do it over here, that T is going to be, and so if I put that in the calculator, T is 4, or T is 5 over 2, 2.5, okay? Okay, so I have 2 different values of T. They both seem plausible solutions, right? They're both positive, they both seem normal numbers, right? And actually both of these are solutions. If you look at the question, it says the times, which are plural, implying 2 solutions, okay? So T is 2.5 or T is 4. Now, why is there 2 values of T? Okay, why is there 2 values of T? Okay, so this is a really good question to illustrate this point here. So, particularly because it's decelerating, and so the acceleration in particular is negative, which means it's slowing down, okay? So we have this positive speed of 13, but because it's slowing down, and because the acceleration is minus 4, that's saying every second the speed is going down by 4. So in 1 second it will then go to 9, then it would go to 5, then it would go to 1. Eventually it will go to 0, okay? And actually it will come to some sort of rest, okay? So the idea is because in particular because it's a negative acceleration, it's slowing down, it's eventually going to stop moving forward. There's going to be a point maybe after A, let's say here, right? Let's say here, this point here, where it reaches 0 meters per second. So it's not moving forwards at all. But what's interesting then is because the acceleration is always negative, it's going to go down, the speed is going to go down even more. It's then going to go to like minus 4 meters per second. Now, how on earth does a negative speed make sense? It's because of the fact it's a velocity, okay? So, velocity, it matters what direction you're in. So, after 0, when the speed reaches 0 at some point here, it's going to turn negative. Now, when it's negative, that means it just goes the other way. So, when it reaches 0, then it's going to speed up and move backwards, okay? Because the direction matters. When we're dealing with acceleration and velocity and displacement, okay, the direction all matters, okay? So when it turns negative, it goes the other way, okay? So that means once it reaches 0 here, it then moves backwards. So we've got this situation where it passes through A at the time when T is 2.5, then it reaches a standstill a bit further ahead, and then it moves backwards. And it moves backwards and it rebounds and it reaches A again, going backwards at T's 4, okay? Hence why there are 2 different times where it passes through the point A. One's going forwards, then the other time is when it's going backwards, back to O, okay? So, that is the idea, that the direction matters, which might lead us to some negatives and stuff like that, okay? So hopefully you understand that point. Okay, so part B, we have, it asks for the value of T t, so the time when the particle, so the object basically, returns back to O. So as we already discussed, once it reaches its sort of maximum, so when it doesn't go forward anymore, when it reaches a standstill, it's going to return backwards, as we discussed, and so eventually it's going to hit back to O again. It's going to round back to O. Okay, so what value of t does that happen? Okay, now, okay, so to work that out again with these formulas here, s isn't actually the distance, remember, it's technically the displacement. And remember, we looked at that before. Displacement, again, cares about direction. In particular here, you can think about displacement of how far have we moved, particularly from the starting point, okay? So if I start at O, again, O to A, the displacement is 20 forwards. That's how much I've walked from O to A, right? But it wants the value of t when the particle returns to O. When it returns back to O, the displacement would be 0, okay? Because it's not moved anywhere away from O, technically. At the point where it returns back to O, yes, it might have moved forwards and backwards. That's the distance. They might have moved distance, but the displacement where they moved, so at that point, how far are they away from O is 0, right? Because it's back at O, it's back at the starting point. So what we're going to say actually is S equals 0 here. When it's back at O here, S is going to be 0. The displacement from O is 0. So I'm going to write it up here. S is 0. Then U, again, U will still be the same. It's 13 if it's going forwards. So U is 13. That starts off at 13. A, again, the acceleration is still -4. V, again, I still don't care about. And T, but T is what I want to work out, right? So again, I'm going to use this formula here. S is ut plus a half at squared. But now I'm going to set S to 0. So 0 is going to be 13t. Add a half lots of -4 lots of t squared. If I simplify this, again, I'm going to get 13t minus 2t squared equals 0. Then I can just factorise. So then I'm going to get t lots of 13 minus 2t equals 0. So that means t equals 0 or 13 minus 2t equals 0. And then if I solve this, I get 2t equals to 13. So t is equal to 13 over 2, which is 6.5, okay? And so there we are. So obviously, when t is 0, that makes sense because the particle starts at O, right? So initially, the particle is at O anyway, so they're not moved anywhere away from O. But when t is 6.5, that's when it returns back to O, okay? When it goes forwards and backwards back to O, okay? So t is 6.5 there, okay? And so there we are. So hopefully you understand that main point of it can go backwards as well as forwards, right? If when it starts to go at a standstill, when it's 0 speed, it then returns back to where it came from, okay? And so that affects sort of the negatives and stuff like that in the opposite direction. Okay, with that in mind, we're going to look at this question, which kind of builds on this a bit further. Right, so in this scenario, we are told a particle is moving on the x-axis. Again, with the x-axis, it's just being fancy for a straight line, essentially. Okay, x-axis is like a straight line, right? And it has a constant deceleration of 2.5. So again, it's going to accelerate negatively at -2.5. Okay, and then at time t is equal to 0. So initially, the particle passes through the origin O, okay, so let's say O is here initially, moving in the positive direction of x, so it's moving forward essentially with speed 15, okay, so they're just overcomplicating it a bit, to be honest, but here we are. So the speed initially is 15. Find the time between the instant when P first passes through O and the instant when it returns to O. So again, we've got this exact sort of situation where, because the acceleration is negative, it's going to slow down. So when it's positive 15 at the start, it's going to slow down to 0 somewhere, okay? It's somewhere here. Okay, and then it's going to return back, and then it's going to speed up and go and move past O again, okay? We want the time when that happens, okay? So again, if it returns back to O, right? If it returns back to O, the displacement is 0, right? The displacement is 0. So I'm going to set S to 0 because there's not the instant it passes and goes back to O, they've not technically moved anywhere away from O. Okay, so the displacement is 0. Okay, make sure you understand the crucial difference between displacement and distance. Okay, so S, my displacement is 0. U again is 15. A is going to be no, V. Sorry, V I don't care about. And I don't know. So, and A, the acceleration is minus 2.5. And T is again the unknown. I want to work that out. The time is what I want to work out. So, okay, again I'm going to use the same formula I used last time. So S is ut plus a half at squared. Oh. Okay, so S is 0. So then ut is going to be 15t. Add a half, lots of minus 2.5, lots of t squared. Okay, so then if I expand this, simplify it, I get 15t. Then half of minus 2.5 is minus 1.25 t squared, set to 0. Okay, so then I can factorise. So t lots of 15, take away 1.25t equals 0. So t equals 0, or 15 take away 1.25t is set to 0, so that means 1.25t is equal to 15. So then t is 15 divided by 1.25, which will get me 12. Okay, and so we're going to take this solution, right? That's when it returns back to O. So obviously initially t is 0 because it starts at O, so again it's not moved anywhere away from O if it starts there. And then 12 is when it is the time when it returns back, okay? So time is 12 when it returns back. And so that's the answer. So the time between it first passes through O, which is here at the start, and then when it returns, that time must be 12, okay? Okay. Then it says for part B to find the total distance travelled by P, the object, right, during this time. Right, so the total distance. So now again, this emphasises again that displacement is different to distance. So in that same time frame, in that same journey, obviously it starts at O, it moves forward, then it goes to a standstill at some point here, and then it moves backwards, and then it'll pass through O again. Now it wants the distance. So as I discussed, the displacement is 0 because it's not moved anywhere away from O. If it returns back to it, okay? But the distance, obviously, it has moved and walked somewhere forward, right? It's moved forwards and then backwards. So it has travelled distance, but the displacement is 0 overall. Anyway, so what's the distance? So, again, as we discussed then, it comes to a standstill at 0 meters per second at some point here. Okay, so that I do need to be aware of that. I need to be aware it will slow down to 0 at some point in order for it to move backwards. So that means if I first consider this, right? If I consider this journey as time as t1, the first part of the journey, then it moves backwards at 0, and then it moves at some speed here at the end. I can split this up into two journeys, right? Into two journeys where it starts at 15 and then it comes to rest. And then it starts to move backwards from 0 speed, and then it ends back at O. Okay, so if I call this point P then, actually no, they've already used P. Let's use A. I don't know. Let's use the point A to represent the point where it goes to 0 speed. Okay. Now, right now, what we can find firstly is the distance from O to A. Okay, when it goes forwards from O to A. Okay. O to A. So then the distance, so the displacement, well, from O to A, it's moved a distance from O to A, right? And so the distance is what I want to work out there. So the distance is a question mark. U, my initial speed is again 15. Okay. My velocity, again, the key idea is the velocity has to go to 0. Right? If it comes to rest at some point, it comes to a standstill. And then A, the acceleration is again minus 2.5. And T I don't care about, okay? Right. So, okay, which formula does not include T? Okay, I don't care about T. Which one of these 5 formulas here doesn't involve a T? Here, right, this one here, V squared is U squared plus 2AF. So that's what I'm going to use. Okay, so if I sub my values in, again, I'm going to call SX, just because I don't want to confuse it with with a 5 or something like that. Okay. So then V squared is 0, is going to be 15 squared, add 2 lots of minus 2.5 lots of X. Okay, so if right. So okay, so then if I simplify it, 0 is going to be, well, 15 squared is 225. And then minus 5 lots of X, right? So therefore 5X is 225. So therefore X is 225 over 5, which is 45. So that is 45 meters. So that is the distance from O to A, right? That is the distance O to A. And this is the maximum distance, okay? This is the maximum distance the particle travels, right? Because when it goes back to 0, it doesn't move any further than that. So that is sort of the maximum distance it can reach. Then it obviously it goes backwards after that. So this is a maximum distance, and with maximum distance, you always want to consider the velocity to be 0 at the end of the distance. Okay, when it comes to a standstill. Right. Well, actually, if the distance O to A is 45, then obviously it returns back from A to O. It goes backwards in the same way. Then the distance is just going to be another 45, right? We're just going to add 2 lots of 45, right? If it goes from O to A, then back from A to O, and it returns back to O, well, then the distance is going to be 2 lots of 45, right? Because it travels 45 forwards, then 45 backwards, okay? So total distance is 2 lots of 45, which is 90 meters, okay? And there we are. Okay. Hopefully it made sense. That could be a bit, especially for the first time, that can be a bit of a sort of weird idea. I don't know. But hopefully it made sense of how I considered the velocity at the end to be 0 when it reaches this standstill, right? And then it goes backwards, okay? Right. And so that's it. Okay, so we're going to look at some exercise questions then. Right, so here we're told a particle is again moving on this x-axis. Again, a fuddy sort of name for a line, essentially. It's on the line. On the next axis with constant deceleration 5. So again, the acceleration is 5, but negative 5, because it's a deceleration. At time t0, the particle passes through the origin O. So again, let's say O is here. With velocity 12, so it moves at 12 meters per second in the positive direction, so it's going to move forwards, right? At time t seconds, some time t, the particle passes through the point A, okay, with x coordinate 8. Now, if the so-called x coordinate is 8, again, if it's an x-axis, think about an actual x-axis. The origin, is 0, right? And at A is 8. So actually we can infer from that the distance between the 2 points is literally 8 meters, okay? Right. Okay. Then it says oh, that's really it. So then it's asking for part A to find the values of t. So the values of t, so t is when the particle passes through A, okay? So again, the values of t Well, again, it's the same sort of situation because it's slowing down because the acceleration is negative. If it starts at 12, it's going to slow down, and eventually, some point, say here, it's going to go and come to a stop at 0, and then it's just going to go backwards, okay, and move backwards. Anyway, but for now, all we need to find is t when it passes through A. So again, it's going to go forwards, then it's going to come backwards. Okay, so if we consider this, what we've got here, if I use SUVAT, then, well, if we want the distance from O to A, as we just discussed, the displacement is 8. Okay, the initial velocity is 12. V, well, the velocity at A we don't know anything about, and we don't really care about it. The acceleration is -5. And t is what we want to work out. Okay, so we're going to be using the formula without a v in. Okay, we don't want v in, so we're going to be using this formula here. S is ut plus a half at squared. So, okay, so then 8 for s is going to be 12 lots of t. Plus a half lots of -5 lots of t squared. Okay, and so then if I simplify, okay, 8 is 12t, and then a half of -5 is -2.5 t squared. Then if I just move everything to the left, I get 2.5 t squared minus 12t add 8 equals 0, and now we've got a quadratic, right? So if I solve this quadratic, if I state the formula, t is going to be 12 plus or minus the root of -12 all squared. Take away 4 lots of 2.5 lots of 8. All over 2 lots of 2.5. And so if I put that in the calculator, I get t is 4, or t is 0.8. Okay, so again, two sensible values, and these are my solutions. Okay, so t is 0.8 and t is 4. And again, that means when it passes through A the first time, when it moves forward, firstly, that's when t is 0.8. Then obviously it's going to come to rest here. Then it's going to move backwards. And then when it moves backwards, that'll be at time t is 4. Okay, so that's the idea. Okay, then it says for part B, to find the velocity of the particle as it passes through the point with x coordinate -8. So if this is positive 8 from O to A, again think of it like an actual x-axis, if you will. Well, -8 is going to be the other direction. So if I extend the line backwards, -8 is going to be there. Okay. And again, why is the distance negative? Because it's not actually distance, right? Because it's displacement, because it's going in the negative direction. If I said forwards here is the positive way, then backwards, if it's going backwards, has to be a negative, okay? Because remember, direction matters with these measurements here, okay? Right, so then the velocity as it passes through the point here, so if I call that, I don't know, B, right? Then it wants the velocity here, so v ms to the -1. So what's the speed here when it passes through B? Right, well, I still know that originally when it moves forward at O, the initial velocity is 12. I know the acceleration is -5. I also know obviously v, but I also know that the displacement, so how far away are we from O, our starting point O, we're actually -8 away because it's backwards by 8, okay? So I'm going to say my displacement, firstly, for my SUVAT, my displacement is -8. U, again, my initial speed is 12. I also know that my final velocity, that's what I want to work out. A, my acceleration is -5, and I don't care about t. Okay, so I want the formula without a t in, which is going to be v squared is u squared plus 2as. So v squared is going to be 12 squared, add 2 lots of minus 5, lots of minus 8. And so that would be v squared. If I put that in a calculator, I get 224. So therefore v, if I just root both sides, is 4 root 14. Or as a decimal, 14.97 meters per second to 2 decimal places. Okay, so that is my answer. So the velocity as it passes through this point B, where it's -8 away from O, the velocity is this number here, 14.97. But I'm going to also specify it's backwards, okay? Or to the left of O, okay? Make that distinction about the direction. So this speed, I'm saying it's speeding and moving backwards to the left. It's not moving to the right, it's moving to the left, okay? So I'm specifying the direction of the speed, okay? Or you could just say the velocity is at negative 14.97 meters per second, right? Without specifying it's backwards, because the negative sign means it is going backwards, right? Because again, velocity has a direction. So if forwards is positive, right? So here is positive 12 speed. If we're going backwards, then the speed has to be negative, right? So you can just specify it's negative to mean it's going backwards as well, okay? Okay, so we've got this question here, slightly different. So here we're told two particles now, P and Q, so 2 different objects moving. They're moving on the same line with constant acceleration 2 and 3.6 meters per second at time t0. P passes through A, so blah blah blah. Okay, so what's going on here is essentially we've got 2 different things moving. What I'm going to do is kind of do them separately then, alright? So firstly, this is going to be P, so the movement of this particle P. So what we're told about P is initially t0, P passes through A, so we start at this point A with speed 4, okay? We're also told the acceleration, right? So t, the acceleration is 2, okay? So and the good news is the acceleration is positive, so we don't need to consider if it moves backwards because it will always just be moving forwards. If it's positive, it'll be speeding up, so the velocity will always be going bigger. It will get bigger and bigger, speed up and go faster. It will never move backwards. Anyway, so the acceleration is 2. And that's all we're told for P. Right. And it's saying for part A to write down an expression for the displacements, okay? So in terms of t, so the time after A. So again, if we have some time A, time t, right? If it moves, and let's say it's at this point here, away from A, it has a distance, right? It has a distance of displacement. So the displacement, I don't know what that is, okay? I also don't know the time, but they told me that the time is t, okay? Now, that's all I know about P, right? So it wants me to work out the displacement, right? In terms of t. So I'm going to need to involve time. So again here, if I do my SUVAT, again, S, I don't know. That's what I want to work out, the displacement from A. So kind of the distance from A, right? U, initially the speed is 4 and the acceleration is 2, okay? And V, I actually don't care about V, the speed at some point in the future. I don't care about the final speed. T is T for time. Okay, so which one does not include V? It's going to be S, this one here. S is UT plus a half AT squared. Okay, so right. So if I substitute my values in, so that means S is going to be 4t add a half lots of 2t squared. So if I simplify, I get 4t add just t squared. Okay, cool. Now, okay, now we're going to consider Q. Okay, so now we're going to do the same for U. So if I draw what are the information given, so again it's on the same line. I'm not going to do both of them on the same diagram. I think it'll make it a lot messier. So I'm going to split them up. So again, the acceleration of Q is now 3.6. So again, it'd be moving forwards, it'd be speeding up because it's positive acceleration. So it will not be moving backwards. I'm also told, the speed of Q when it passes through A, the speed is 3. Okay. So again, at A, the same point, it's 3 meters per second. Right, and it's the same sort of story. They want me to work out a displacement, right, in terms of time t. Okay, so the displacement, so how far away are we from A? I'm not given an endpoint, but they just want me to find a sort of generic displacement formula, right? Displacement formula in terms of time. Okay, so the time, right. So they want it in terms of t. Now, what we're told about Q is it's 1 second later. So that means Q is 1 second ahead. No, 1 second behind Q. P, sorry. Q is 1 second behind P. Okay, which means if P is moving at t seconds, Q, if it's 1 second behind, has to move at time t minus 1. Okay, t minus 1 second. If Q is 1 second behind P, because Q reaches A, the same point 1 second after P, so it's 1 second behind. So the time is t minus 1. Okay, hopefully that made sense. So what I can say here is, again, the same sort of stuff. The displacement I'm going to call just S, right? I don't know my displacement. U, well, initial speed is 3. V, I don't care about. A, the acceleration is 3.6. And time is t minus 1. Okay. And so again, then I'm going to use the same formula: ut plus a half at squared. And so if I sub my numbers in, S is going to be 3 lots of t minus 1, not t, add a half of 3.6 times t minus 1 all squared. Okay, so if I simplify this, I get x, s is 3t, take away 3 if I expand in this bracket, and then a half of 3.6, that's going to be 1.8. And then this bracket, if I expand t minus 1 squared, that would be t squared minus 2t plus 1. And so if I expand that again, if I expand the 1.8 in front, that's going to be 1.8t squared minus 3.6t plus 1.8. And so if I clean this up, I get 1.8t squared. Then 3t take away 3.6t is minus 0.6t. And then I have minus 3 plus 1.8, that'd be minus 1.2. So that's my final answer. Okay, so there we are, right? I guess technically what I should do as well is that the P's displacement, so the displacement of P is going to be different to Q because they're on different journeys, right? So I'm going to say S of little p, okay, to represent displacement of P, and the same for Q. Okay, so SQ. Okay, hopefully you're with me there, right? SQ. Okay, there we are. Right, so those are those two displacements. For only 2 marks, pretty mean. Then part B says find the value of T when the particles meet. Okay, the value of T. So when the particles meet, that means obviously they're going to be at the same point, right? So if this is x here, let's say they meet at point x. That's the same point, right? Point x. So if we measure from A in both of them and the same point x, right? These 2 points are the same in the both journeys, so the displacements will be the same. The distance they both travel from A to x, right? If they both meet at x, that means the displacements have to be equal here, okay? If that makes any sense. So when they meet, obviously they meet at the same point, so this is P, this is Q, let's say. So their displacements have to be the same if they both start from A, right? So we can set these two displacements together, right? So the displacement of P and Q, okay? So part B, SP has to equal SQ, the displacements of both, okay? That's a common sort of strategy. If you're given a scenario where two things meeting or colliding together, you're going to want to consider their distances to be equal, okay? So if we do that then SP, which is 4t add t squared, that's going to equal SQ, which is 1.8t squared minus 0.6t minus 1.2. So then we just solve this quadratic. So if we move the left to the right, then we're going to get 0.8t squared by subtracting t squared. Then if we subtract 4, we get to subtract 4.6t minus 1.2 equals 0. Then we solve this quadratic. So we're going to get t is 4.6 plus or minus the root of minus 4.6 squared, take away 4 lots of 0.8, lots of minus 1.2 over 2 lots of 0.8. And so if I put that in the calculator, I get T6, or T is minus 0.25. Okay, well, obviously this makes no sense. T cannot be negative. T has to be positive. So T must be positive because it's time, right? You can't have negative time. So therefore T has to only be 6. So that is the time when the particles meet. And we know we're right because it's only one value they want. Okay, so we're probably on the right tracks, right? Then part C says from the distance from A when they meet. So again, so it's this distance here. If they both start at A and they both end at X where they meet, what's the distance or the displacement? Well, that's what these formulas are doing, right? They're giving me the displacement from A. So if we have the time, right, where they meet, we can substitute that simply into just either formula, right? So I'm going to sub, very simply, from the distance, I'm going to sub T6 into, let's say, the displacement formula for P, right, which we found in part A. So that, again, the displacement formula gives the displacement away from A at any time T. So we know the time they intersect, that they meet, right? Then we know that then this will give me the distance to where they meet. Okay, so if I substitute this into SP, so 4t at t squared, so therefore T6, we're going to get SP is going to be 4 lots of 6 add 6 squared. So that will get me 60. Okay, 60. So that is my distance. Okay, there we are. Okay, so we're going to look at some exam questions, and we got this one first, which is probably weirdly the easiest question I think we've seen in this video for an exam question. So here we're told a car is initially at rest on the road. So if we again draw a little diagram, so if it's at rest initially, the initial speed is just going to be 0. Okay. Then it accelerates with constant acceleration of 3.2. Okay. And then it wants to find firstly the speed after 5 seconds. Okay, so let's say if we start here and then end at this point here, it has a final speed, right, of v, let's say. So the time we're given to be 5 seconds, okay? So very simply then, if we list our SUVAT, S, well, we don't care about S here, the distance, displacement. U, we start with 0, the speed. V is what we want to work out. A, the acceleration is 3.2, and the time we're given to be 5. So very simply, which formula does not include S, sorry, it's this top one here. V is U plus AT. Okay, so at that point we sub in to get V is going to be 0, add 3.2, lots of 5. And so if we work that out, which is 16 then meters per second. Okay, fairly nice. Right, then part B, it wants the total distance travelled. So now the distance, right? What is the distance? So at that point now, if we go back to SUVAT, now we do want the S. We do want the S, the distance. U is again 0. V, I do know it's 16. That's fine. A is 3.2 again, and T is 5. Again, I'm given it's 5 seconds. Well, really, I'm spoilt for choice here because I have all 5 quantities here. Well, obviously, I want to find S, but I'm dealing with all 5. Okay. So I'm spoilt for choice. You can pick pretty much any formula as long as it has S in. Let's just take this one here then. S is UT at a half AT squared. Okay, so S then is going to be 0, lots of 5, add half, lots of 3.2, lots of 5 squared. And so if I put that in a calculator, I get 40. Okay, so that'd be 40 meters for my distance there. And so there we are. Okay, cool. Okay, we've got this more complicated exam question. So here we're told a car is moving along a straight road. Again, let's draw a little road, a little line, with constant acceleration. There are 3 points A, then B, then let's say C here. Okay, where A to B is 22 meters. Okay, let's label that on. And B to C, the distance here is 104 meters. Okay, the car takes 2 seconds to travel from A to B. Okay, so I can say also the time here is 2. And also the time from B to C is 4. Okay. So it looks quite, I guess, nasty, just 7 marks, but they've kind of laid out the information in a weirdly nice way. So it wants the acceleration of the car. So again, it says it's at constant acceleration, so I'll just call that A, okay? And that's what I want to work out. And also the speed of the car the instant it passes through A. So at A, which is my starting point, this will be my initial velocity, U, right? So it wants these, it wants A and U, essentially, okay? Right, so what are we going to do here? Well, what we do know is, well, we want to find A and U, okay? So if I list my SUVAT, right, I'm not going to list what I have, but I'm going to say S, U, V, A, and T. I want U and A, okay? I want U and A. I need both of them. Okay, so what I can do here is, if my initial speed if I have to start with U, right? Let's start at A, right? So firstly, let's consider A to B, right? Let's just consider the journey A to B. So my distance, my displacement is 22, right? It's moving forward by 22. V, now the final velocity, if it was to start at A and end at B here, this would be my velocity. I'll call that VB, right? But I actually don't care about that because I know my time as well. I know my time is 2. Okay, so what I can do here is, if I want a SUVAT formula that doesn't involve a V, So it's going to be this one here. S is ut plus a half at squared. Okay, so if I sub my values in, I get 22 is going to be ut, so 2u, add a half lots of a, lots of 2 squared. If I simplify that, I get 22 is 2u, and then 2 squared is 4, 4 times a half is 2, so 2a. Okay. Then, again, it's the same story. I still want a SUVAT where I got my initial speed u, so I want to start at u, so I'm going to have to start at a again, and I want my acceleration a. So what I can consider instead, if I want to still start at a, but I want a different journey, obviously I can't consider a to b, because I've already done that. What if instead I consider the whole journey from a to c, right? Because I can work out the overall, or the total distance and the time as well. So my distance then from A to C, well, it's 22, add 104. So 22 add 104, which gives me my distance from A to C. My total distance, that's 126, right? So 126 here. U is again U. V I don't care about. A is A, and my time, I can work that out. Because if I add the 2 times, 2 and 4 is 6. So overall, it takes 6 seconds from A to C. Okay. So again, hopefully you can start to see what we're going to do here. Okay. Simultaneous equations, I think we're going to end up in. So again, I don't have a V in. I'm going to use the exact same formula. So S is ut at a half at squared. So then 126 for S is going to be 6u add a half lots of a lots of 6 squared. So then if we simplify this, we get 126 is 6u, and then 6 squared is 36. 36 up a half is 18, so 18a. So what do you notice? I've got these two equations. These are simultaneous equations in u and a, right? So if I list them then, so I've got 2u and 2a firstly. That's going to equal 22, was it? Yes. So that's my first equation. And then I've got 6u add 18a is 126. Okay. Now, when we progress more into mechanics, you'll see a lot of questions do involve simultaneous equations. So do kind of try and have that in mind with certain questions. Okay. So here, well, it's just simultaneous equations. So at that point, is even back to GCSE, right? Just to solve these, you could put it in your equation solver. But sometimes the mark scheme are a bit fickle. Sometimes they want working. Sometimes they don't. Sometimes they usually should specify it though. But it's it's very good to be safe than sorry, right? So if I quickly try and solve these simultaneous equations. Well, what I can do is notice I can try and eliminate maybe u, right? Because I've got 2u here and 6u here. They're nice multiples, right? In order to eliminate, say, u, I need to match the coefficients. So if I want 2, if I want to get from 2 to 6 here, I need to times the top equation by 3, okay? So if I do 1 times 3, I'm going to get 6u and then 6a. It's going to equal 22 times 3, which is 66, okay? Now, hopefully you notice what I can do here is I can take these two equations away. So if I take the second one take the second equation from this bottom one here, by 6u take away 6u is 0, 18a take away 6a is 12a, which is 126, take away 66, which is 60, okay? So therefore a 12a 60, divide by 12, we get a to b 5. Okay, and there we are. That's my acceleration. Then simply I can find u by substituting a back into either formula. So if I sub a back into, say, the first equation, so into this top equation here, then I'm going to get 2u add 2 lots of 5 equals 22. And so therefore 2u add 10 is 22. So then 2u is going to be 12, so therefore u is 12 over 2, which is 6. And that is my value for A and U, or in other words, the acceleration and the speed initially at A. Okay, so there we are. Nice 7 marks there.